Hi everyone, my name is Alan and this is the first episode of the Intelligence Podcast. I work in artificial intelligence and I'm very interested in discovering about ideas that could help take the world to a better place. In this episode, I got interested about the subject of longevity and extending the human lifespan. I invited Dr. Aubrey de Grey, the founder of the Longevity Escape Velocity or LEV Foundation and one of the leading voices in the field. The first time I heard about Dr. Aubrey de Grey was around 2006 when he gave his TED Talk and argued that humans might be able to live to hundreds of years in the near future. Fast forward last year, I had the chance to meet Dr. Aubrey de Grey in a small pub in Cambridge City in the UK, and I had a long chat with him. I asked him about his work, about the longevity field in general, about the recent progress, about the role of AI, and about his predictions of when humans are going to be able to live longer. If you want to know about his responses to my questions, I invite you to watch this interview. So let's start by trying to give some hope to people watching this. And here I mean by hope, like giving some positive predictions or let's say expectations about the future of aging research. So you famously coined the term longevity escape velocity, so LEV. So what is LEV? This would be my first question. And when do you expect the humankind to reach it?
Yeah. Okay. So in order to answer the first question, what is longevity escape velocity? I need to give a little bit of background. The work that I've pioneered over the past 20 or more years is all about developing treatments that will address aging and keep people healthy for longer. But the specific thing that I have pioneered is the idea of doing that by repairing molecular and cellular damage. Whereas before I came along, the focus was all on trying to minimize the rate at which that molecular and cellular damage is created without actually getting rid of damage that's already been created. Now, that's a really important thing to bear in mind, because if you're slowing down aging, in other words, slowing down the creation of damage, then somebody who is already in middle age and, has nearly enough damage that is going to make them get sick fairly soon, then you're not going to be able to delay their getting sick by very much. But if you repair damage, then you can buy a lot of time. So this is where the longevity escape velocity concept comes from. The idea is that we can develop, let's call it first generation damage repair therapies, rejuvenation therapies, which will take somebody who is aged, let's say 60, and turn them back to being 40 or so that they won't be biologically 60 again until they are 80, let's say. Now, that can be repeated over and over again, but if you use the exact same therapies, then the impact, the benefit will go down because the therapies will not be perfect. There will be types of damage that they do not work on. And that means that in order to really continue to rejuvenate the same people over and over again, we will need to keep improving the therapies over time. And so the question is, how rapidly? But that's what longevity escape velocity is. It's defined as the minimum rate at which scientists like myself will need to continue to improve the comprehensiveness of these therapies after we get to that first point where we get maybe 20 years of extra life. So then you're asking the question, how soon do we expect to get to that first 20 years? That's something that people have called the Methuselarity. That's not my word, but I like it. Basically, I think that at the moment we have a 50-50 chance of getting there within the next 12 to 15 years. So really quite soon. Now, of course, that's only a 50-50 chance. I completely accept that, as with any pioneering technology, there are a huge number of ways in which we could be delayed. And I would say that there's at least a 10% chance that we won't get there for 100 years. But who cares? 50% chance is quite enough to be worth fighting for.
Yeah, so this sounds to me like a surprisingly optimistic prediction, actually, or a view of the future. It kind of, for someone who is, let's say, not specialized or just like watching media to know about what's happening, it feels like things are not really moving that fast. And your prediction says it's like within 12 or 15 years. So this kind of imply that there's something happening now that is waiting just to be released. Is that the case? Is that the reason behind this optimistic prediction?
Almost. So essentially, the reason why it sounds over-optimistic right now, in contrast to what we can already do, is because damage repair is a divide and conquer approach. In other words, we have to be able to repair a lot of different types of damage. We don't necessarily have to repair any of them perfectly, but we have to repair all of them fairly well in order to get this postponement of age-related chronic conditions. And at the moment, the only way to judge how soon we're going to get there and to look at, to make these predictions is by going into all the details, which is, of course, what I do. I'm at the coalface. I am, constantly looking at the progress that's being made and evaluating how much more progress needs to be made to get such a thing to work. Now, a large part of my belief that we are only 12 to 15 years away revolves around my belief that we are within only 3 or 4 years, with, again, 50% probability, of achieving a similar amount of progress in mice. Now, in mice, we will not get to what I've been calling longevity escape velocity because they age so fast that we won't have time to improve the therapies and so on. But if we get a really big improvement in the longevity, and especially the healthy longevity, of mice that we start treating when they are already in middle age, so let's say 2/3 of the way through their normal lifespan, then we very much can expect that the world will sit up and take notice. And that, the war on aging will really begin in earnest. That we will have a very great acceleration in everything that happens in translating such results to humans. And that means not only a much greater amount of funding for the relevant research and clinical trials and so on, it also means a complete rebuilding of everything that goes after that, the regulatory process and also the building of infrastructure, of training of enough medical personnel, things like that. The reason we can be very sure that that will happen is because governments are focused really on money. And of course, on getting re-elected. And once there is widespread public appreciation that we are within striking distance of bringing aging under proper medical control, it will be impossible to get re-elected unless you commit to doing this, right? Plus, the economic benefits will be absolutely astronomical, as many people have published and discussed for decades. The only reason why those economic arguments have not been effective so far is because they only work if we can actually make progress in postponing aging. And at the moment, people are continuing to believe that we can't, whereas these mouse experiments will change that. So that is really why in my new foundation, LEV Foundation, our number one focus is on achieving that extension of healthy mouse lifespan.
Okay, so does that, let's say, timeline also includes the constraints coming from regulatory process like Fed approval of certain drugs, or it needs a revolution in that process?
Absolutely, it does include that. I just mentioned regulatory processes will have to be very dramatically revised, but let's remember, the regulatory process is a result of legislation. It is what elected people say it should be, and it can change when they say it should change. So yes, this will be genuinely like wartime, where decisions are made rapidly and dramatic changes happen very quickly if they are seen to be necessary.
So let me take a step back after giving this prediction to try to explain a little bit some of the basics to the problem, like why we think we can't conquer it. So you famously came up with the 7 sense pillars or landmarks, and you suggested that the aging mechanism is maybe too complicated to try to repair, to intervene at the level of the process itself. We need to repair the damage. So you coined, or you stated, 7 types of damage that we can attack. So first question, how is that different from geriatrics, which also repair damage in a sense?
That's a really great question. And in fact, a large part of why I took several years to convince my colleagues in the biology of aging that my way of looking at how to address aging made any sense was precisely because they could not really see the difference between damage repair and geriatrics. So what is that difference? Ultimately, it comes down to really one big thing, namely geriatric medicine attacks the pathologies of late life directly. In other words, it tries to treat them a bit like infections, really, and eliminate them from the body. But it does not address the underlying accumulating molecular and cellular damage that caused those pathologies to happen in the first place. And since that damage is still accumulating, that means that any geriatric medicine, any medicine that tries to address the consequences of that damage, is inevitably going to become more and more ineffective as the person gets older. Now, a lot of people get this wrong. Gerontologists often say that the main real problem with geriatric medicine is that so many different things go wrong with us late in life, and they go wrong at more or less the same time, so they interact with each other, they exacerbate each other, and it's just too complicated a problem. That's not really true. I mean, it is true that a lot of things go wrong, and it makes it a very complicated problem, but that's not what makes the problem inherently intractable. So what does make it intractable is when I said that you're addressing the consequences of something that is still accumulating.
Yeah, so the way I understand it, you are kind of addressing the very late consequences, because damage is a consequence in a sense, like the damage you are suggesting.
Let me make sure you have this right. Geriatric medicine addresses the late consequences. Damage repair addresses the early consequences, the first things. So, in other words, the things that metabolism is generating all the time, starting even before we're born, but which are initially harmless until they have reached a level of abundance that is beyond what the body is set up to tolerate.
That's a really nice way to view the problem, like late versus early consequences. So let's talk a little bit about these 7 sense pillars or landmarks. So 2 of them are intra and extracellular aggregates, which are 2 types of damage. What are those?
So inside the cell, that's intracellular, there are various types of material that are created as byproducts of normal metabolism and that just accumulate because the cell does not have any way to break them down or to excrete them. And different cells accumulate different types of such stuff. So, for example, the main cause of blindness in the elderly is something called macular degeneration, which is caused by the accumulation of a particular molecule called A2E. This is a molecule that is a byproduct of the chemistry of vision. It's occasionally formed as a result of the process that absorbs light. And it just accumulates, and eventually it kills the cells that it's accumulating in, which are called the retinal pigmented epithelial cells. In the artery, it's a completely different problem. You've got the accumulation of oxidized cholesterol. And this happens in a type of white blood cell called a macrophage. And that's what drives atherosclerosis. Macrophages are very good at doing the job they mostly do, which is to recycle cholesterol. They could do that forever, but they can't recycle oxidized cholesterol. So again, we have to get rid of that stuff. In the brain, there are various types of material that accumulate. For example, in Alzheimer's disease, there's something called neurofibrillary tangles, which are mainly composed of a particular protein called tau. And again, this is probably important in the progression of Alzheimer's. There's different things in different places. Outside the cell, it's a bit different. Most of the stuff that accumulates is a bit like tau. In other words, it's made of proteins rather than other molecules. And one example, again, in Alzheimer's is amyloid beta. There's another type of amyloid that is made of a different type of protein called transthyretin, and that accumulates in the heart. There's another one in the pancreas, and so on. So all of these things need to be got rid of. But the reason I described these things in only 2 categories out of my 7 categories is because we really can apply just 2 methods. I had, back then, 20 odd years ago, I was talking about how we could identify enzymes in other species that would break down things inside the cell, and how we could activate the immune system to break things down that are outside the cell. Both of those things have gone well, and there are, actual examples of these therapies that are either already in the clinic or they are very close to clinical trials. Moreover, there are alternative approaches to these things that have been developed. For example, one of the companies that was spun out from SENS Research Foundation is pursuing an approach to getting rid of oxidized cholesterol in the artery that does not break it down, it just extracts it and causes it to be excreted. So you get the idea.
I believe here, even if there are 2 types or intracellular, like it's 1 type, I believe every type of damage in different organ maybe or tissue needs a different maybe research program or method.
Kinda. The reason why the classification into these 7 categories is so important is because, yes, we will need a different therapy for each type of damage, each example within the category, but those therapies will have a lot in common. So we can identify enzymes that break down A2E in the eye. We can also potentially identify enzymes that break down other things. Similarly, we can identify ways to attack proteins in neurons and in the way I just described. The idea is that the corresponding damage repair approaches are generic. They may differ from one example to another in terms of the details, but only the details. Yeah, the idea, of course, is that once you've got 1 or 2 of them working, then getting the next one working and the one after that will be much faster and much easier because you can reuse the expertise, the knowledge that you gained in developing the first one.
Right, like the family, let's say, of solution is kind of the same. We need just to extrapolate it to other types of damages.
That's right.
One other type of damage, which is kind of similar to, not similar, like in a sense, is senescent cells. So it's a type of waste, but why it's a completely separate category in your pillars?
Right. So the big difference between my original description of this classification of categories of damage versus the more recent things like the hallmarks of aging and so on, these upstart versions, is that these newer versions kind of miss the point, in my view. They are kind of a classification of everything that's the people who work on aging are interested in, but it doesn't have this correspondence to generic approaches to getting rid of the things. So in the case of senescent cells, again, it had to be a separate category because the approaches I've just mentioned for getting rid of aggregates inside the cell or aggregates outside the cell would not apply to senescent cells. You'd have to have a different approach. Back then, the only approach that I knew of that seemed possible was something called suicide gene therapy, which is still being pursued. Maybe the right way to go for certain cases. There's a company named Oshin that we work closely with that is basically doing that. But of course, since I first suggested the SENS classification, maybe 10 years ago or 12 years ago, there was this enormous breakthrough where people started to find that there were drugs that could selectively kill senescent cells. These are now called senolytics, of course. And so, again, this is something where the problem has become easier over time.
Okay. Let me move to another type of cells, which forms a fourth category, which are stem cells. So this is a very known, let's say, term. Many people at least heard of it. But why this is on your 7 pillars? What's the problem with stem cells?
Right. So initially, again, going back 20 years, my feeling was that the main problem was that there are certain types of cell which are not automatically replaced by cell division when they die. And this causes certain aspects of aging. So the most easy one to describe is Parkinson's disease, which is caused by the death of a particular type of brain cell, a type of neuron called the dopaminergic neurons. And they're not replaced, so we all lose them. Some people lose them faster than others, and eventually some people don't have enough of those neurons to make this important chemical dopamine. So the idea would be to replace these neurons artificially by injecting stem cells that were of the right type to divide and differentiate to replace the cells that the body is not replacing on its own. And that's definitely an important aspect of stem cells, the stem cell problem and the stem cell solution. However, now we know more. First of all, we know that you can inject stem cells for other reasons. And indeed, they don't even need to be stem cells from the same person, so they may be attacked by the immune system. But in the meantime, before they get destroyed by the immune system, they may do good just by secreting nice stuff. So that's not really the category I was talking about in SENS. It's just another way of delivering molecules that may have beneficial effects. On top of that, though, we've now got this amazing thing called partial reprogramming, which was only developed quite recently. And here the idea is, again, we increase the number of stem cells in the body, but we don't do it by injecting them. Instead, we do it by somehow turning back the developmental clock of cells that are already in the body and that used to be stem cells and have become less stem-like. We reverse that and make them more stem-like again. And there may be some risks associated with that approach. There are still plenty of experiments that haven't yet been done, but it's definitely a promising alternative.
The last one I would like to talk to among the SENS pillars is the cancer problem, let's say, the cancerous cells. So when I first read about this, it felt a little bit surprising to me as someone who is not specialized, why this is classified as damage rather than an intrinsic mechanism, let's say, or something that just happens and maybe it's very difficult to prevent it. So what makes cancerous cells a type of damage in your theory?
Well, I mean, first of all, it's damage because it kills you. You know, the more cancer cells you have, the more likely you are to die because cancers grow, right? But secondly, of course, the real problem here is the cause of the cancer, the accumulation of damage to the DNA, which makes the cell misbehave and divide when it's not supposed to. So yes, of course it's damage. I mean, it accumulates with time, right? Nearly all cancers are age-related. They happen to older people much more often than to younger people. So of course it's damage. I guess you want to ask about how we're going to go about it. And again, we have good news. Originally, 20 odd years ago, I came up with an extremely elaborate and ambitious and really, perhaps not really even realistic approach to addressing this, involving elimination of the genes that allow cancer cells to maintain their chromosomes when they divide. And this would have to be done by somatic gene therapy, and it would have to be very thorough, very difficult thing to do. But now we have two things that have come along to improve on this. First thing is that a group in Texas developed a fantastic drug that kills 90% of cancers in humans very easily by essentially exploiting the way in which they maintain their chromosomes. The thing that I wanted to simply shut down, instead, the cell can be actually killed because of that thing not being shut down. This is the enzyme called telomerase. The company is called Maya. I should say that I don't have any financial interest in it whatsoever. I just think it's the most promising cancer therapy in the world right now. Greatly deserves to be supported. They're just recruiting for a phase 2 clinical trial right now, but they should be doing far more than they have the money to do. So this is something that I really believe in. The other advance is much better known. It is in cancer immunotherapy. 20-odd years ago, cancer immunotherapy was definitely a research area, but it wasn't making any progress. There was people have been trying for years and years to improve the ability of the immune system to get rid of cancers, and it was incredibly slow going. But then about 15 years ago, I suppose, there were two really huge breakthroughs. The development, number one, of something called CAR-T, and number two, something called checkpoint inhibitors. And both of these approaches have massively improved our ability to activate the immune system against cancers. They've completely transformed the treatment of some cancers, and they are making continued progress. So cancer immunotherapy, again, is something that's looking really good.
So are we talking here about prevention methods that they are therapies that are applied to healthy people to prevent the outset?
So, I often call damage repair the sweet spot between prevention and treatment, because it is treatment in the sense that we are taking someone who's in middle age maybe, and we are turning their body back into something similar to how it was at an earlier age. But it's also prevention in the sense that these people typically will not yet be sick. They will not actually be exhibiting the pathologies of late life. So it's a bit of both, if you like. It depends on your definition.
So you mentioned earlier partial reprogramming. Can this be one type of, let's say, method to also address this? Because the mutations accumulate over time. So if we kind of how to say it, to move in the other way, to move backwards and reprogram the cell to be younger, is that something even makes sense?
No. First of all, partial reprogramming does not do anything to mutations. It only changes the epigenetic state of the cell. In other words, the chemical changes around the DNA, not the DNA sequence itself. And mostly cancers are driven by changes to the sequence itself, actual mutations. Secondly, to the extent that some cancers are largely driven by epimutations, in other words, undesirable changes to those other chemical modifications, even there, partial reprogramming is a very indiscriminate thing. So it may help some cancer cells that are already cancerous, but it may do the opposite. It may take cells that are not cancerous but are a bit fragile because they've got some mutations that are making them nearly cancerous, and it may actually disrupt the remaining machinery, the epigenetic machinery that is stopping the cell from becoming totally cancerous. So that's a risk.
So these are some of the types of damage. Now let's move to some of the solutions. So what can we do about this? So when you thought about these 7 pillars, you also thought about what you called SENS, strategies for engineered negligible senescence, right? So these are strategies. So every type of every pillar cause of aging is associated to one strategy. But before going to those strategies, let's talk about what we can really do about it. So these are types of damage: waste, stem cells, etc. Are there any way to reduce this damage significantly by radically changing our lifestyle, like our food regimes, our sport regime, etc.?
So unfortunately, there seems to be very little that we can do with diet or lifestyle to slow down the rate at which the body generates the damage that eventually makes us sick when we get old. The best way that we have is what's called calorie restriction, which, of course, has been studied in the laboratory in rodents for nearly a century, and which does pretty well if you're a mouse or a rat. We can get mice or rats to live 40 or 50% longer than they normally would, just by feeding them less than they would like. But unfortunately, the impact on longer-lived species is much less than the impact on short-lived species. And at this point, even if you start early in life, it seems highly unlikely that calorie restriction would give more than 2 years of additional postponement of the health problems of late life. Now, That does not mean in any way that we should just neglect calorie restriction. It seems to me that, even a month of additional life is worth having. And if you're the kind of person who does not find it too difficult to do calorie restriction, then, it's a quality versus quantity thing. Furthermore, of course, these days, there are a number of drugs out there, of which perhaps the gold standard at this point is rapamycin, that are able to trick the body into thinking it's in a famine when it isn't, and thereby give us something like the best of both worlds, cause us to live a bit longer, even without the inconvenience of having to eat less. So this is a very valuable area of research. But the key thing we have to bear in mind is that it's definitely not the fountain of youth. It will only give us a relatively small increment in how long we can stay healthy.
What about sports? Like calorie restriction is about how we eat. What about if we exercise a lot? Is there any equivalent effect known to us?
Exercise is certainly good for you in the sense that it postpones sarcopenia, the loss of muscle mass. This is just an example of the general principle of use it or lose it. The more that you make use of the functions of your body, and this, of course, applies cognitively as well, the more you will keep the body youthful. But, of course, keeping good muscle function is only one part of giving good overall function. So there's only so much that exercise can do. Certainly, it is a good idea to do enough exercise to make sure that you don't get seriously overweight. And of course, that is a very different amount of exercise from one person to another. I'm one of those repulsively lucky people. I don't need to do any exercise at all, and still nothing happens. But you need to do as much exercise as your body tells you need to do.
So what's actually the fundamental reason these techniques, especially about calorie restriction, work better for mice than for longer-lived mammals or other species?
Yeah, so this is something that's really easy to understand from an evolutionary perspective. And I was quite shocked 20 years ago when I saw that my colleagues were essentially ignoring this and sweeping it under the carpet and talking over-optimistically about the idea that humans might theoretically get the same proportional increase in lifespan if we could just figure out how to do calorie restriction exactly right. Essentially, the evolutionary logic is very simple. It just arises from the fact that in nature, in the wild, which is where evolution happens, long famines are not so frequent as short famines. And the frequency of an environmental circumstance is what determines the strength of the selective pressure on evolution to develop metabolic optimizations to address that particular environmental circumstance. If something happens often enough, then it means that if there is some kind of metabolic optimization, adaptation, that one could theoretically have to respond to that environmental situation, then the animals that evolve that adaptation will do better and pass on their genes more frequently than the animals that have not adapted in this way. Famine is definitely one of those things. Famine is something in which it is better to readjust one's metabolic priorities in favor of optimizing maintenance and hunkering down, so to speak, at the expense of reproduction, which is, of course, a very energetically expensive process. Whereas when you're not in a famine, the best thing to do is to reproduce as soon as possible before you get eaten. And as a result, we have across the whole of the tree of life, certainly across all mammals, the ability to respond to famine by adjusting our metabolic priorities in that way. But, as I said, long famines don't happen very often. And that means that the selective pressure to respond to be able to live 10 years longer or 20 years longer in response to famine just has never happened. We have not had the selective pressure, so we don't have that machinery. Our machinery to respond to famine, if you like, it's less impressive. The metabolic acrobatics that we have evolved, that we still have genes for, is less impressive than the metabolic acrobatics that mice or rats or other short-lived organisms have. And of course, we can go further down the tree of life. If we look at nematode worms, you can make them live 10 times longer than they naturally would. Certainly, even just by natural calorie restriction, you can make them live at least 5 times longer than they naturally would if you starve them at just the right time in their life cycle.
So it really seems like this is a mechanism that is, let's say, programmed in us. We don't really have that control on it. So, okay, so lifestyle is not the way out. You mentioned rapamycin, so this brings our discussion to the supplement type of solution. So we talk a lot today about rapamycin, about metformin, about NRs. So what is your take on these?
So the various molecules that have a lot of prominence right now as potential anti-aging molecules, such as rapamycin and metformin and NAD precursors and so on, these all act in one way or another as calorie restriction mimetics. They have different mechanisms of action, but one way or another, they act to somehow trick the body into thinking that it's not getting as many calories as it would like, even though it is actually getting as many calories as it would like. And the idea here, of course, is to induce the cells in the body to behave in the same way that they would in a famine, which, as we know, in mice and rats, is life-extending. It postpones the health problems of late life. So this is why they're interesting. But the key thing is that we would never expect that any calorie restriction mimetic would do better than calorie restriction itself, because it's simply turning on the same pathways that have evolved to optimize our metabolism in the context of actual famine. And as such, we definitely have no reason to suppose that any of these drugs, whether ones that already exist or ones that may be developed in the future, will give more than a few months to a year of postponement of the health problems of late life when they are initiated in adulthood, or especially not if they're not initiated until middle age.
So what about metformin?
So metformin is a molecule whose main mechanism of action is to slow down the respiratory chain. It's believed that metformin interacts with the first step of the respiratory chain, called complex 1, and essentially inhibits its activity. So this, of course, is easily seen to be a way in which the body is tricked into thinking it's not getting enough calories. The respiratory chain is a step in the process of making ATP, and ATP is, of course, the energy currency of the cell. ATP is created as a result of the electron transport chain combining oxygen with nutrients in order to extract energy from those nutrients, which is then funneled into the proton gradient at the mitochondria, and that is used to make ATP. So if you're not doing enough electron transport, then you won't make so much ATP, and the rest of the cell won't see the details of that. It'll just see the output, the readout, which is not enough ATP, and it will do exactly the same thing that it would do if the reason you didn't have enough ATP was a different reason, namely not having enough nutrients.
I heard about the TAME trial. You also mentioned it in a book I read. There was an interview with you. You mentioned the TAME trial by the FDA. Do we have the outcome of this? What's that trial in the first place, and do we have its outcome today?
So first of all, the TAME trial has not yet begun. Second of all, it's not going to be performed by the FDA. The big thing about the FDA in relation to the TAME trial is that the FDA have approved it. Basically, what that means is that they have said that if it reaches its clinical endpoint, then they will approve metformin as a drug to be used against aging in general. Now, if you read the fine print, you will find that they don't really use the word aging, but they agreed with Nir Barzilai and his colleagues who are going to be performing this work on a definition of the clinical endpoint, which is aging in all but name, but it's concretely enough defined that it can be used as a yes-no clinical endpoint, which is, of course, what the FDA needs. It was a huge task to get that far, simply because people who work on the biology of aging have such a hard time agreeing on what aging really is. I think that's ridiculous. I think it's perfectly obvious what aging is, but this was a very hard thing to do, but it's been done now. So yes, the TAME trial is very important in that regard, simply because it shows the way for other people to develop other treatments against broad-based treatments against the damage of aging. Whether the TAME trial actually succeeds, or indeed even whether it actually gets conducted, is not really the main point, because nobody's going to make any money out of metformin. It's been off patent since before I was born. But what matters is that it takes a lot of money to get a drug far enough along to be in a clinical trial at all, and that money has to be invested by a big pharmaceutical company, for example. They're only going to do that if they know that they're going to get their money back in the long run because of the drug being actually approved by the FDA. And now all they need is to create a clinical trial with the same clinical endpoint that the TAME trial has, and they know that the FDA are not going to push back.
In any way, since metformin is meant to simulate caloric restriction, you do not think that this will really be a major element in LEV, right? Longevity, escape velocity. This will make us maybe gain 1 or 2 years, but not that much.
That's right. There is no way that any calorie restriction mimetic, whether it's metformin, rapamycin, or anything, can ever give more than calorie restriction itself gives.
What about NRs?
So NR and NMN are these two famous molecules that are precursors of NAD. And NAD is a very important molecule in cellular metabolism. It's also a kind of currency that shuttles stuff from one place to another. So ATP basically shuttles energy from one place to another. What NAD does is it shuttles electrons from one place to another. And one critical thing that NAD does is it shuttles electrons into the respiratory chain. So when I was talking about complex 1 a moment ago in relation to metformin, the rate at which complex 1 does its thing is inhibited by metformin, but it's also dependent on the cargo, on the material that complex 1 processes, and that material is NAD. Specifically, complex 1 receives 2 electrons from a molecule of NAD and transfers them one at a time through a lot of complicated internal machinery, and eventually transfers them onto a molecule called ubiquinone, and then it carries on down the electron transport chain. Now, that means that if we have a reduction in the amount of NAD, then we will have a reduction in the rate at which complex 1 can do its thing. So again, we will have a reduction in metabolism. That sounds like reducing NAD would be a good thing, but actually it's a lot more complicated than that, because NAD does so many different things in the cell. And so actually it turns out that the amount of NAD that we have in the body goes down with age, and there's pretty good evidence of a variety of different types saying that this is a problem, and that if we have more NAD, then we're healthier. One theoretical explanation for that, which I rather like, is that the purpose of NAD, as I said, is to carry electrons around from one place to another. So you can think of NAD as an electron reservoir. And one way in which the cell detects whether it is receiving enough calories is to detect what proportion of the NAD in the cell is carrying electrons. Some of it will be carrying electrons and some of it won't. That's why it's a reservoir. And if you put in a whole bunch of extra NAD, you're not changing the total number of electrons that the cell is going to have in that reservoir. So that means you are changing the average, if you like, the proportion of the reservoir that's full, because you've got the same amount of stuff in a larger reservoir than what you had before. So the cell can, again, detect that and misinterpret it as a shortage of calories. And I believe that that's a very plausible mechanism for how NAD supplementation works. But you can't take NAD itself because it's not absorbed, so you take these precursors, NMN or NR, which are converted by the cell into NAD, and it amounts to the same thing.
Okay, so it's another, let's say, trick to simulate caloric restriction in a way. So same, like we cannot count on this in order to, let's say, to live hundreds of years, like to reach life. So the only way out, as I understand it, is engineering, is biotech. If I understand,
I believe so.
Like we need SENS, the strategies for engineered negligible senescence. Okay, so about these strategies, we are not going to talk about all these strategies. I'm just going to get interested in one or two of them, especially nuclear mutations. So again, nuclear mutations they cause cancer. Let's say one of the reasons behind some types of cancer. What is the engineering technique that we can use in order to stop the consequences of this type of damage?
Right. So as I mentioned, I believe strongly that if we can completely cure cancer, then we just don't need to worry about nuclear mutations or epimutations, because it will take many times the currently normal lifetime before those mutations rise to the level of abundance that is bad for us in ways other than cancer. So, what is my approach against cancer? Well, first of all, let me say that I am extremely optimistic about the potential for cancer immunotherapy to do the job. And we don't work on cancer immunotherapy because, of course, masses and masses of other people are doing that. But even 20 years ago, I was always having leaders in that field come and speak at my conferences because I knew that it had the potential. And then suddenly, 10 or 12 years ago, there were a couple of really huge breakthroughs in cancer immunotherapy that took it from a real backwater that wasn't getting anywhere into something that has made huge strides. There was the development of CAR-T, chimeric antigen receptor T cells, and also the development of checkpoint inhibitors. And there's a long way to go, though, but cancer immunotherapy is certainly continuing to improve rapidly. And there are certain other new technologies that are being combined with the ones I just mentioned to achieve that. So I'm very optimistic that cancer immunotherapy may be enough to bring cancer under complete control. However, in addition to that, I am very interested in manipulating the telomere in order to address cancer. Telomeres get shorter when a cell divides, and the only reason why cancers get away with that is because they activate mechanisms that compensate, that re-lengthen telomeres. If a cancer doesn't do that, then it never gets anywhere near big enough to kill us before everything dies, all the cells die. And so I'm interested in ways in which we can stop cells from developing those mechanisms, or perhaps in some other way make the mechanisms problematic. The first approach that I suggested for this 20 years ago was essentially to remove the genes that the cancer cell activates in order to activate this mechanism of telomere lengthening. And that was a very, very ambitious idea, very challenging. A lot of people said it'll never work. And, I accept that it's really hard. But now there's a kind of second generation version of that that's being taken forward by a company in Chicago based on a drug that was developed by a group that we work closely with in Texas. And that drug essentially turns the enzyme that lengthens telomeres, this enzyme telomerase, into a suicide gene. It essentially causes cells that are making a lot of telomerase to kill themselves rapidly. And this is an extraordinarily exciting drug. It seems to have a great potential to address 90% of human cancers, and it's already recruiting for a phase 2 clinical trial. So I'm very, very hopeful.
So when it comes to cancer, I kind of feel that SENS, like the strategies you're proposing, they are kind of similar to the philosophy of geriatrics, just when it comes to cancer, but to cure it at a more fundamental level. But we are not trying to touch on the mechanism creating mutations, let's say, on the first place. It's like kind of attacking the cancers itself, or like more fundamental mechanism for cancer.
Yeah, I mean, normally I give this very simple description of aging as you've got metabolism, it creates damage, the damage accumulates, eventually the damage causes pathology. But that is a simplification. Clearly, what's really going on is the kind of network of chains of events, right? And that go from metabolism at the beginning to pathologies at the end. And all we need to do is break that network. So it doesn't matter. We don't need to be particularly religious about saying we have to make our interventions happen right at the beginning of the chain of events. If it turns out to be easier to go one step further along the chain and attack them there, then that's fine.
Yeah, like to be more pragmatic. Like if we can win some years, let's say, of lifespan by using these techniques, so why not? So what about reprogramming or partial reprogramming? Is it a way to address the same problem?
So partial reprogramming is a really, really clever idea that was first pioneered by a great friend of mine, Manuel Serrano, in Spain. He looked at the concept of induced pluripotent stem cells, which had been developed back in 2006 by the Japanese group of Shinya Yamanaka. And he said, well, what do you want? Can this thing be done in the body, in vivo? And he just did it as a proof of concept at first. He just made mice that were overexpressing these 4 famous genes that Yamanaka had identified. And sure enough, it did work. Cells in the animal were taken backwards to a point where their developmental clock was turned back so that they were behaving like embryonic stem cells. Now, of course, that was very bad for the mice, and Serrano knew that it would be. They developed a lot of a particular type of tumor called a teratoma, which is what happens when a cell is so primitive that it doesn't know what to do, so it does everything. But then the next step was another researcher out in San Diego did the obvious next step, which was to control how much of these genes was expressed. He created a system where he could express them, let's say, for 1 day a week or 3 days a week or whatever. And sure enough, it turned out that if you judge it just right, then you can get beneficial rejuvenating effects. And he did not observe any significant side effects, no teratomas, for example. So this is wonderful, and this is really the main reason why there are now a number of big companies putting really serious money into partial reprogramming. However, we must ask the question, is it going to work? Is it going to actually go all the way to a development of a safe and effective therapy for humans? And my personal feeling is it's still very, very risky. We may very well not be able to do that, simply because of how we control cancer. So, of course, cancer is a really complicated phenomenon in which cells accumulate a whole bunch of mutations that allow them to escape from the normal control of the cell cycle and to break down the extracellular matrix and so on and so forth. And because it's a multi-step event, in other words, our cells have to accumulate a lot of mutations in order to become cancerous, that means that even by early adulthood, you and I have plenty of cells that have already got most of those mutations, just not all. So in other words, essentially, then you can think of each cell that's not dividing, that's sitting in this quiescent state, this healthy cell, as having a kind of what I like to call a cytostatic cage. So that means basically a network of processes and signals and so on that combine to ensure that the cell does not divide when it's not supposed to. And these mutations that are accumulating in our cells constitute essentially partial breakage of that cage. The cage becomes less strong, more fragile. So when you do partial reprogramming, what you're doing is you're whacking that cage with a sledgehammer. And cells that have a more fragile cage already, some of them, the cage will just collapse and the cell will just start to divide uncontrollably. And it's very, very difficult to know whether that has happened. In mice, for example, they just don't live long enough. You just won't know whether you created cancers by doing this. So this is the problem that I have right now. Now, there are two ways out of this. One way is to cure cancer. So we talked about that a moment ago. If we can get, for example, this business of making telomerase into a suicide gene, if we can get that to really work, then yeah, we can afford to play much more fast and loose with therapies that are regenerative, but also potentially pro-cancerous. And the other approach is to develop a different way of doing partial reprogramming, a way that involves different genes that we might overexpress that might push the cell back into a more regenerative state, but not as far as the Yamanaka factors do. So not far enough to make them really lose identity and become cancerous.
So that's why we call it partial, right?
Right. Partial reprogramming, by definition, is when you make the cell more regenerative, but you don't make it lose its identity. And the problem with the Yamanaka factors is that even if you try to adjust the level of expression or the frequency of expression, you're doing it to a bunch of cells that are not all the same. Some of those cells will be pushed too far by the same amount that doesn't push other cells enough.
So when you apply all of these techniques, let's say biotech or like engineering technique, from partial programming to like targeted therapies, how do you measure the impact or the advantage, or let's say the surplus of the years you are gaining by applying these therapies? How do you assess your work?
Yeah, great question. So, of course, lifespan is a consequence, a side effect of health span, right? We just know that, people tend to die from being sick. And these days, most people get sick from being old, from having been born a long time ago. So what we'd like is to be able to measure the impact of rejuvenation therapies quickly, without having to wait to see whether the person dies, or even really to wait too long to see whether the mouse dies. At the end of the day, though, we do have to find out that fundamental readout, and that's why Longevity Escape Velocity Foundation is now embarking on this very impressive and expensive experiment with 1,000 mice to combine 4 different therapies in a manner that will, with any luck, get some serious postponement of aging. But absolutely, we want to get more information as quickly as possible, whether it's in mice or in humans. And for that reason, we are measuring all manner of different types of health span, of biological function. There are lots and lots of things that can be used in this regard. Of course, one of the most fashionable ones right now is epigenetic clocks, which look at the state of the epigenome. But there are also much more direct ones, functional ones, like grip strength and, there's something called the rotor rod, various ways to measure cognitive biological age as well. And we're doing all of these things, as well as measuring a lot of different things in the blood of these mice, a lot of different, we're going to be killing a few of the mice every so often and doing stuff that you can't do unless you kill the mice. So we're measuring many, many different things. And the hope is that we will see statistically significant differences between different groups of mice that are getting different types of therapy really quite soon. way before we can get statistically significant data on longevity, on lifespan.
But we're still, like, mostly we are still measuring this progress on mice, right? Like, this is the measure or the main method we use today, right?
We are definitely still using mice as the main model organism. And of course, it does make sense to use an organism that lives not very long so that you can get the final readout in not many years. But also, of course, the reason why mice are so popular is because so much of the details of any biological experiment revolve around optimizing of techniques. And that is very species specific. If you try and use a completely new species, you've got a whole bunch of wheels to reinvent before you can really do these experiments. Now, saying that, of course, everybody knows that the probability that something will work in humans, if it works in mice, is pretty low. That things don't translate very well. But the reason why people persist and carry on doing these mouse experiments is because the chance of something working in humans, if it works in mice, is definitely greater than the chance of something working in humans if it doesn't work in mice. So yeah, we know that there are limitations to how much we will learn, but we still want to learn it. And of course, there's also let's call it the rhetorical motivation for doing mouse experiments. If we can find a panel of treatments that we can give to mice at middle age, like 18 months of age, which is when we are starting this experiment, and we succeed in doubling their remaining lifespan. Normally, these mice would live for about another year. If we can get that out to 2 years, that's huge. Then it will be impossible for any so-called philosopher or, troublemaking commentator to say that aging is somehow completely different from diseases and it's like gravity and medicine will never be able to do anything significant about it. People just won't be able to say that anymore. And that is going to make a huge difference to the political acceptability of putting serious public money into making sure that we actually get to be able to treat humans sooner rather than later.
So from assessing the efficacy, let's say, of therapy, let's move to assessing progress since you started, let's say, talking about longevity or like spreading the word. So let's say 2000, how do you see the progress since then?
The progress has been huge from the conversation point of view. I became high profile in the media and in the conference circuit in the mid-2000s. And back then, a lot of people seemed to be interested in what I was saying, but nearly everybody viewed me as more entertainment than science. They basically said, obviously we don't really see, any particular holes in Aubrey's logic, but we know they're there because we know that aging is not a disease. We know that aging is like gravity and there's nothing that we'll ever be able to do about it. Therefore, we're not going to pay any attention to this, even though we don't have a good reason not to pay attention. And that pretty much carried on being true in the wider world until the Hallmarks paper came out in 2013. As soon as that paper came out, first of all, the conversation within the biology community was over because these were extremely credentialed people essentially restating what I'd said a decade earlier, and they were published in one of the top journals in the world. The paper rapidly became by far the most highly cited paper this century in the whole of the biology of aging. And, I have never since that day needed to justify the damage repair approach in the community. But also in the wider world, the wider world became aware that this was a mainstream, respected and generally, accepted concept that aging was actually something that we could do something about. And, it went from a situation where top people in the field were just, essentially prohibited by the political environment from even talking about doing something about aging to the point where it was more or less the opposite, where you had to talk about aging or you had to talk about doing something about aging or you didn't seem credible. So that change has been enormous. But of course, there's still a huge way to go. We've still got masses of people out there trying to pretend that aging shouldn't be cured. That we should, that it would be too disruptive to the natural order and things like that.
Yeah, so I think maybe part of this might be because there is progress, but it's still the kind of progress that seems to be behind the scenes to the public. Like there is progress, but there's no drugs yet. We cannot yet do anything about our
That is absolutely
lifespan.
right. That is absolutely
so it
right.
still seems like, yeah.
Yeah, I mean, fundamentally, people know in their heart that aging is absolutely ghastly. And they also know in their heart that aging is a medical problem, something that potentially medicine can bring under control. But they also know that medical research is research, and therefore that we don't know how soon medicine will bring aging under control. Even people like myself who are out there giving honest, concrete time frame estimates. My estimates are probabilistic, right? So people just, mostly don't want to get their hopes up. They find it psychologically easier to carry on pretending that aging will never be under medical control and that it's just something we have to, get over and, live with and find and come to terms with, rather than getting emotionally invested in the possibility that they might actually live long enough to benefit from these interventions. And you're absolutely right. Every single little step that is taken in the laboratory, whether it's our laboratory or anybody else's, that brings this closer is a step towards people finding the courage within themselves to not think that way anymore, to not try to convince themselves that aging is a blessing in disguise or anything like that.
Exactly. So yeah, to take the leap and like to leave the belief in the certainty that we are going to die. So okay, so this is acceptability, progress on acceptability. What about on the engineering aspects? Do we have blockers? Like, are there some of the SENS, let's say, strategies that are easy, like going faster than others? Are there ones that are completely blocked, like difficult to treat?
There's always been a pretty wide spectrum within the SENS categories, among the SENS categories of difficulty. So at SENS Research Foundation, we've basically never done any work on stem cell therapies, simply because that was already moving pretty fast in a lot of different people's labs when SENS began. And similarly, we have progressively moved away from emphasizing other areas within SENS, not necessarily whole categories, but at least subcategories, because, again, they've moved far enough along that investors start getting interested, and we've been able to spin projects out of startup companies. Investors write bigger checks than donors do on the whole, so that means that we can kind of make it no longer our problem. But absolutely, there are things at the more difficult end of the spectrum which are still very much pre-investable. That's why I still believe that nonprofits play a huge role here. And over the past couple of years, we've seen a really welcome and enormously valuable increase in the amount of purely philanthropic support for this work, coming especially from certain really big hitters in the cryptocurrency community, which has been transformative, really, in terms of speeding things up. So if I look at where things are now on the most difficult end of the spectrum, there are definitely things that need to catch up. One of them is mitochondrial mutations. Another is stiffening of the extracellular matrix, which is an area that has not received nearly enough attention from the community over the years. Both of these things, even I'm going to say 5 or 6 years ago, were not going well at all. We'd really not made perceptible progress until then. But both of them kind of had big breakthroughs around that time. And even though there's definitely still a long way to go, they are now moving forward. The stiffening of the extracellular matrix led to us being able to spin out a company called Revel Pharmaceuticals, which is well funded now and is forging ahead. Just very recently, another company was created in that space. So this is definitely a happening thing now. Mitochondrial mutations, similarly, there are a few companies now trying to achieve one part of that problem, which is using what's called mitochondrial transfusion. And there are certain things that those companies are not yet doing that we believe is necessary, but SENS Research Foundation is pursuing those bits that are missing. So again, I'm much more optimistic now than I was even 5 years ago in that regard.
Okay, so let me ask you about your opinion about some of the major or main works that are happening in other labs. David Sinclair recently published his work on the information theory of aging. So what do you think about this theory? Does it align with the 7 pillars of aging and SENS, or it's like completely another
Yeah, certainly it aligns. So I will say that I don't like the idea of theories of aging. That's the kind of language that gerontologists historically used a lot, and it's become much less fashionable lately. And I think that's a very good thing, because nobody ever really says what they mean when they talk about a theory of aging. And I think it's just confusing language. So I kind of wish David had not reverted to that kind of language. But in terms of the actual mechanism that he's talking about, the idea that there could be an accumulation of nuclear DNA damage resulting from the maintenance process in various ways, that's certainly a very valid, very logical approach. The only thing I would say is that it's the same as every other type of mechanism for accumulating nuclear DNA damage, in the sense that, again, the main consequence is going to be cancer. So again, if we can address cancer, then we don't need to address that mechanism that David is talking about any more than we need to address any other mechanism for the accumulation of nuclear DNA damage.
Yeah, so this, let's say, the solution for that, like the epigenetic maintenance, would only address, let's say, one element of SENS, one pillar, which is nuclear mutation, but it won't solve intracellular waste or senescent cells or stem cells. This is not a solution for this type of things.
Well, so no, it's not a solution. But let me, since you asked it that way, let me emphasize the importance of crosstalk. So when I'm going to say 12 years ago, when the first papers started coming out looking at the benefits of eliminating senescent cells in mice, and this was, of course, not using senolytics back then, it was using a specially engineered genetic model. People were very surprised, very pleasantly surprised, and certainly I was, at how widespread the physiological benefits were in these mice. People had thought about the idea that senescent cells might be actively toxic rather than just not doing what they were supposed to do. And Judy Campisi first put that idea forward in the late 90s, and that's a large part of why it was part of my original SENS scheme. But back then, we were thinking that, okay, really the main benefit in terms of their toxicity will be that they are procancerous, that they are secreting things that will make nearby cells that are already precancerous, tipping them over the edge into being properly cancerous. And we still think that's true, but it seems that the toxic impact of the SASP, the secretory phenotype of senescent cells, is much broader than that. And so, it could very well be that this crosstalk, where repairing one type of damage has knock-on effects, benefits on the rate of accumulation of other types of damage, that could be a lot bigger than we know. And so, in the case of David's mechanism of the accumulation of DNA damage, it's possible that there could be knock-on effects like that, but it's very much too early to say. This recent paper that came out, David had a lot of very good data showing that if you accelerate this mechanism, then that's bad for mice. Okay, fine. But he only had very, very preliminary data showing the opposite, showing that if you slow down the mechanism or antagonize it somehow, then this is beneficial. He just had a little bit of demonstration of that in cell culture at this point. So there's a long way to go to show that this actually has benefit.
Okay, so we really need to understand the effect of treating one type of damage on the others, and I think this will
let me stop you there.
like.
Let me stop you there. We don't really need to understand it. No, we just need to try it. So in the case of the work that we're doing at ICOR, this big combinatorial mouse experiment, we're taking 4 different interventions, each of which individually has been shown to have a benefit on lifespan, both mean and maximum lifespan, when started late in life, around 18 months or older, and we're putting them all together in various combinations. So we don't know which ones are going to work, and we certainly don't have, well, there are certainly different ways that we could predict based on different theories. We honestly don't care. We're just doing the experiment, and what works, works.
Okay, so more experimental approach to it. Okay, so let me ask you about some of the opinions I heard about the whole idea about addressing or trying to attack on the mechanism of aging and, let's say, the damages. So I recently watched a interview with Charles Brenner, and his opinion was that aging is an emergent phenomenon. There's no clear mechanism for aging. So every effort to address that mechanism is really hard to give fruit. And also we are trying and experimenting on mice, and we are evaluating using clocks, epigenetic clocks. So we don't really know if this will be beneficial to people. We don't have a generation yet that lived longer than what they should. So we don't really know what we are doing. What's your opinion on this?
Yeah, so Charles has made a bit of a reputation for himself over the past couple of years as a professional cynic within the community. He is a relative newcomer to the community. He was basically, dragged into it when David Sinclair especially started publishing work on NAD precursors, because that's his field. He works on NAD metabolism, and he has made some important contributions there. But he came in not knowing much about aging, and that didn't stop him from saying a lot of things. And, he basically, points out, he makes a bunch of valid points about how much we don't know. And then he kind of tries to pretend that we are somehow ignoring the fact that we don't know these things, when we're not actually ignoring it at all. We know damn well that what we're doing is difficult. We just feel that it's worth trying. And so, people are not really paying much attention to Charles these days.
I also think that one answer to this might be the way you thought about the 7 pillars. Like, the mechanism is very complex, but we don't need directly to attack on it. Just look at these pillars and try to do something about the damage. So I feel that the SENS theory in itself is kind of an answer to this question. Another critique I read recently by a French medical doctor called Alain Fischer. He works here in France. So he talked about mutations, nuclear mutations. The accumulation of mutations is a driver of, let's say, what we said, cancer and other diseases. So he said, even if we can treat some of the, consequences, we will end up having too much mutation. Let's say we live for 100 years. We will reach a threshold where the mutation would cause not only cancer, but maybe other diseases. It will be a complete mess if we don't treat these mutations, and we don't know how to treat them. What do you think about this? I think it's quite interesting for me.
It's not interesting at all, because it's exactly what I've been saying since forever, that for the moment, we can get away with just treating cancer, and it will take a long time before mutations and epimutations accumulate to the point where they matter in other ways. Eventually, they will matter in other ways, but eventually is a long time in the future. So the fact that we don't yet know today how we would address those problems is a very stupid reason not to do what we can do today.
Okay, so the idea actually, if we can treat all types of damage, let's say we reach a level or a point where we can treat all the 7 types of damage, this is not going to make us live by itself. I mean, let's say 1,000 years. This is to buy time until we know how to attack on the complex mechanism of aging.
Right. So this again is the longevity escape velocity concept. If we can address all of the 7 types of damage reasonably well, then we will buy ourselves a couple of decades of additional healthy life. And the same people who received those therapies will then be able to come back 20 years later and receive version 2.0 of damage repair, which will be able to repair some of the damage that version 1.0 could not repair, and so on. So, we will develop more and more versatile, different approaches to addressing these various types of damage, and we will stay ahead of longevity escape velocity. Even today, we can see that different types of damage can be addressed by different types of damage repair, by a wider range of types of damage repair than I was saying 20 years ago. I gave the example earlier of senescent cells, which back then I thought we were going to have to address with suicide gene therapy, and now we find that we can actually just use simple drugs and get rid of these cells fairly selectively. And that will, similarly with eliminating molecular waste products. Back then, I was thinking only in terms of enzymes that break these things down, and now we have examples of cases where we can actually promote the excretion of the material rather than breaking it down at all. And then even with extracellular waste products, originally I was thinking we've got to immunize against this stuff and get the stuff inside cells so that it can be broken down there. We now have also methods for breaking down the material outside the cell without getting it inside. So, the range of options that we have is increasing all the time.
Right. Okay. So I would like to talk a little bit about your own contribution to all this. So if you can describe your trajectory. I know you had the SENS Foundation. I know you have a new foundation now. So can you talk a little bit about your own this trajectory?
Sure. So for sure, my main contribution to the field over all these years has been to introduce the concept of damage repair as a more pragmatic, more practical approach to postponing the health problems of late life than the alternative of making the body run more cleanly and generate damage more slowly. But in addition to that, I've made a number of specific ideas that I've brought forward for how we might do various types of damage repair. Of course, the idea of controlling the telomere as a way of addressing cancer is something that I pioneered. The idea of putting backup copies of the mitochondrial DNA in the nucleus is something that I didn't actually originate. Other people had thought of that earlier before me, but I kind of popularized it. Using bacterial enzymes to break down waste products. These are things that I brought in as new ideas. So I've made a variety of contributions. But over the past 15 years, the main thing I've been doing is community building. Of course, I have been the chief science officer of the various organizations I've been in, so I've been overseeing the scientific work that those organizations have been doing. But most of my time has been spent on stage and on camera, getting people to understand what this is all about, just raising the quality of the conversation and getting people on board. And that has had various motivations, various reasons I've been doing it. Firstly, of course, it's been a good way to bring in new funding for my organization and for other organizations to accelerate the work. And secondly, it changes the conversation at the level of policy making and decision making in the corridors of power. Very slowly, but surely, we are getting people to take this seriously and to understand where money can be well spent to hasten the defeat of aging, and not just the development of these technologies, but also their distribution to society.
Yeah, so as testimony of this, I myself actually knew about the whole possibility of solving aging after your TED Talk. And it's true that since then I start to see an accelerated presence of this type of acceptability and discussion about aging in media and French media where I live now. And I can perceive that contribution actually. What about the LEV Foundation? How is it different from SENS?
LEV Foundation is really a progression from SENS Research Foundation. SENS Research Foundation was created at a time when the whole concept of rejuvenation was still very poorly accepted, when most scientists within the field kind of understood that I wasn't as crazy as they had thought I was 5 years previously, but they hadn't really come on board with it. It was really only in 2013 that was over. So SENS Research Foundation's main job was to make rejuvenation a mainstream thing. And that has happened now. There's still plenty that needs to be done to actually implement a lot of the rejuvenation technologies that SENS is all about. But kind of, in a sense, my job is done when it comes to rejuvenation. Where my job is definitely not yet done is at the level of longevity escape velocity. Most people still think that's a concept that just because its implications in terms of lifespan are so dramatic, therefore it must be crazy, even though they can't see why it's crazy. And so I'm now doing what I do best. I'm going out there and being the tip of the spear and, taking all the bullets, so to speak, and, opening doors for people to walk through. The work that we're doing at SENS Research Foundation is still great, but the work that we're doing at LEV Foundation is a step forward from there. Work that is still considered by most people to be just too ambitious to think about. And, that's why people donate to LEV Foundation, is because, if you want to donate to somebody, if you want to donate to work that is ambitious and audacious, you donate to me, because, I don't do timid.
Exactly. So actually, you're not working on the 7 pillars, right? Or the 7 senses, it's like a new...
That's kind of correct, yeah. I mean, at this point, the pillars are all individually moving forward rapidly. And therefore, the most important thing is the next step, which is to combine them in the optimum way. So this flagship project that we're doing, this huge combinatorial mouse experiment, this is something that nobody else would do, because you're not going to get a nice high-profile paper in Science or Nature from showing that if you combine things that already work, then they still work, and you're also not going to make money out of it, because these things either they're not patented, or if they are, then they're patented by different people, and so there's cross-licensing and so on. So it's not really aligned with the incentive structure of industry or of academia, and that's why it falls to us to do it. It's vitally important. It's the way in which we're going to actually figure out how to combine things in the best way. Someone's got to do it, and it's us.
So when you talk about combine things here, what are you talking, combining what exactly? Sorry if I missed that.
Okay, right. So this project involves combining 4 different rejuvenation therapies. Actually, one of the therapies is not really a rejuvenation therapy. It's a kind of non-rejuvenation control, and that's rapamycin. But the other 3 are damage repair properly. So one of them is blood stem cells, doing a bone marrow transplant of young bone marrow into old mice. Second one is overexpressing telomerase, so as to extend the telomeres, which is something that actually it surprised a lot of people when it was found that doing this in old mice is good for them, because mice make their own telomerase much more promiscuously, but it does benefit, and we kind of understand why now. And then the last one is a senolytic, a drug that specifically kills senescent cells. So we will be, of course, having a control group of 100 mice that are not getting any of these things. We've got 4 different groups, each of 100 mice, that are getting just one of these things as a kind of baseline to understand the benefit and to reproduce past work. And then we've got a group that's getting all 4 of these things combined. And then we've also got 4 groups that are getting 3 of the things out of the 4, so as to be able to identify potential antagonistic interactions where things actually do not combine beneficially.
Okay. You work also on cryonics, right?
Yes. So LEV Foundation has a couple of projects which are focused on cryonics, specifically on improving the quality of cryopreservation. So this means not just cryonics itself, but also organ cryopreservation as a way to address the shortage of organs for transplant. So at the moment, the state of the art of cryopreservation of solid organs, or indeed people, is not very good. Basically, the amount of damage that is done to these organs when you cryopreserve them, over and above any damage they may already have, as a result of being taken from an old person, for example, that additional damage done by the cryopreservation process is very problematic. So one of the groups that we're funding, called Cryonics, is looking at some brilliant technology that appears to be able to very greatly reduce the amount of damage done by cryopreservation, very, very greatly, so that it becomes much more plausible. And the other group is working on ways to rejuvenate organs before you cryopreserve them. So essentially to pump stuff through the vasculature that will kill off senescent cells and other things like that in a more powerful way than you can do in the body. Once you've taken the organ out of the body, if you do this, then you can do it better. And then so you've got a biologically younger organ to cryopreserve. So both of these technologies in combination have the potential to make organ cryopreservation a much more useful thing, a really medically relevant thing.
That's a really interesting line of work. Do you communicate your results? Like, do you publish your results in academic papers, or do you communicate on your website? How can we follow this work, actually?
So historically, SENS Research Foundation, we've definitely published ever since the beginning, ever since we started getting results that were worth publishing, and that's still happening very much. At LEV Foundation, we'll certainly do the same, but we will do more than that. So the big flagship experiment with combining these things, we're going to be putting data out there every couple of weeks on how things are going, on the survival curves, on the results of our various health span measurements. We definitely want people to be excited about this, and so we're much more interested in getting that data out there rather than what will happen in the long, 2 or 3 years from now when we're in a position to actually finish the experiment and publish it. And certainly the same applies up to a certain extent with the cryonics work.
Okay, so you have this really exceptional, broad view of everything happening in the field. You work in non-profits and also on startups, like for-profit organization and companies, let's say. How do you see the role of AI and machine learning in this? Does it have an essential contribution today or in the future?
AI and machine learning have an enormous contribution to medical research in general. I believe that the contribution to longevity research is mostly in the form of contributions across the whole of medical research that just apply everywhere. So, of course, we've seen very recently in the past few years the enormous breakthroughs that were made in this thing called the protein folding problem, which determines the 3-dimensional structure of a protein from its amino acid sequence. That will have the most immense impact in speeding up people's research across the whole of medical research, and that is absolutely true within longevity. Then there are lots of companies now, especially ones that we're very close to, such as in silico medicine, looking at using really state-of-the-art machine learning techniques to identify drugs that will have broad impact on aging, as well as, of course, repurposing existing drugs. Again, there's a reason why in silico medicine is doing so well in terms of getting investment from, big players, and other companies like BioAge doing the same thing. It's because this actually is really has enormous potential. And there will, of course, be occasional cases where there's something much more specific, some bioinformatic approach using machine learning on a particular problem within the longevity arena. But in general, I would say that most of the action is going to be these very broad-based things.
So any contribution to, let's say, in the health sphere would be important in general sense, not only on these 7 pillars, let's say, directly.
Right.
Okay, so the reason I'm asking this question, of course, because I myself work in AI, and I would like to ask the question, let's say, in the other way around, by elimination, let's say. So do you think that it's possible to reach LEV, so the longevity escape velocity, without using machine learning? Is it something that's doable?
Sure, absolutely. We're talking, I mean, all of my work, all of the work in the community is with regard to getting to LEV as quickly as possible. We'll definitely get there sometime, but every day that we bring it forward is 100,000 lives saved. So it's just a matter of going as fast as we can.
Makes sense. I have one reflection about AI also in this sphere. So we started by saying the mechanism is like overly complex, and let's attack on these 7 pillars to buy some time. Now we see like how AI and like reinforcement learning, we recently also saw like ChatGPT and like the enormous advances that we are currently able to do. DeepMind also demonstrating that we can manipulate complex systems with machine learning. Do you think that like this type of techniques could someday help us understand this overly complex mechanism, like maybe simulate it in some way and try to control it?
So the difficulty with the complexity of metabolism is not only at the level of poor understanding of it, it's also at the level of simply the intertwining and interlinkage between the things we want metabolism to do and the things we don't want it to do. Yes, I mean, really, if we look at what's already been achieved by companies like in silico medicine in identifying drugs that are useful, we are seeing the first parts of exactly what you just said, improved understanding based on machine learning of what is of how to discriminate between the things we want metabolism to do and the things we don't want it to do. That's why these drugs work. But in order to actually, get real action on this, to really stop metabolism from making damage in the course of keeping us alive, the question is, are there even in principle drugs that could do that could separate those things that really, really thoroughly, really cleanly? And we have no reason to believe that. All we have is reasons to believe that we can slightly separate them so as to have some modest benefits as a result of that improved machine learning-based understanding. I think that still that's not going to change the fact that damage repair outside of metabolism is always going to be more powerful.
Yeah, so very interesting. And I once watched a interview with Demis Hassabis, so the CEO of DeepMind. So he mentioned that if we reach a point where we can simulate the cells and eventually these complex mechanisms, like following from AlphaFold, we might reach a moment where we can do just experiments, virtual, like simulations, like to do like drug experiments, let's say. And
right.
But I think we really need to buy time before we can do this with the SENS strategies.
Yeah.
Very interesting. Okay. So let me just say some concluding questions. So people who are listening, how they can help, let's say. Is there any way like the public or like people who are listening can help?
Yeah, so when people ask me how they can help, my answer is always in the form of a question, because different people can help in different ways. Obviously, if someone's wealthy, they can contribute financially. If someone is a biologist, they can choose which fields to go into. If someone is a journalist or a podcaster, they can interview me and so on. But sometimes it's not completely obvious how somebody can contribute. So one thing that I was able to seed fund last year, and which has had an enormous impact already, is a workshop, a kind of retreat that was run last year called Less Death. So people can have a look at that, lessdeath.org. The second iteration of that retreat is actually happening right now. And there's going to be 4 of them this year. It was a massive, massive success. And the purpose of this retreat was to help people answer that exact question of yours. How can they help? So the people who would come there, maybe 50 people who had a wide variety of different skills and track record and so on. And the purpose was to educate them more, to tell them, to teach them things they didn't know, but also to put them together, to bring people together and create partnerships and alliances and syndicates and so on. And that was just massively successful, even at the first attempt. I've been doing that kind of thing, of course, myself for a very long time. People come to me, I often will introduce them to other people that they can work with, but that doesn't scale. And this is a way of scaling that. So that's why I was so enthusiastic about helping it to get going. Everyone's different. The first thing to do if you decide you want to make a contribution to this field is write to me, and I'll tell you how to. I'll guide
Ask
you.
the question. I would be glad actually to share any links about these events with the interview for people to check out.
Sure. Lessdeath.org is definitely best. Of course, you can go to levf.org, my foundation's website, and that's where to find all of this information.
Aubrey de Grey, thank you very much for these valuable insights.
Well, thank you very much for having me on the show.